please? Okay, so remember what we were in the middle of doing? We were proving the theorem that if S is an ordered set, and S has the least upper bound property, then in fact S has the greatest lower bound property. Right? So whenever you have a set with the property that whenever a subset has an upper bound, it has a least upper bound, you also have the property that whenever a set has a lower bound, it has a greatest lower bound. Okay, so that's what we're in the middle of showing. I hope everybody is on board. Okay, so, and the proof, you recall, was to, just to set things up, suppose you have some subset of S, and it's a non-zero, it's a non-empty subset of S, and suppose B has a lower bound. Suppose B has a lower bound. We want to show that B has a greatest lower bound. And what we did was we said, well, consider the set L, which is the set of all lower bounds of B. Right? Let L be the set of all lower bounds of B. Right? And we observed that this set has an upper bound, right? L has an upper bound, right? What was an upper bound? Why did it have upper bounds? Well, because any element of B was an upper bound of L, right? Any element of B, the elements of L are all lower bounds of B. So any element of B, right? Any element of B is 1. Right? Any element of B is an upper bound. And so by the least upper bound property, there exists a supremum. Okay. So we can assume that we know that there exists a supremum because this guy is not empty, it has an upper bound, and we're in a set which has the least upper bound property. Okay? Okay, and our claim was that that this supremum was the greatest lower bound of B. Right? Was the greatest lower bound of B. Okay. Okay. So first part we need to show is that that the supremum actually is, so part 1, let's show that the supremum of L actually is a lower bound of B. Right? Right? So why is that true? Why is that true? Well, what we said before is that any element of B is an upper bound of L, right? Any element of B is an upper bound of L. Well, this is the least upper bound of L, right? So you saw any element of B, any element gamma of B is an upper bound of L, right? So, right, this being the least upper bound, it's going to be less than it, right? Right. So anybody in B, well, the supremum of L is going to be less than it. So the supremum is a lower bound of B. Okay, is that clear? Am I going too fast? I'm kind of hyped up a little bit. Okay, close your eyes for a second. Raise the finger if I'm going too fast. Raise the finger if I'm going too slow. Okay. I'm going to slow down a little bit. Okay. I'm going to slow down a little bit. So remember what we're doing, right? We've got the set of lower bounds of B, right? The set of lower bounds of B. We've got we've got the supremum of that set, right? The least upper bound of the set of lower bounds of B. And our strategy is to say, well, that's probably going to be the greatest lower bound of B. Okay. So to show this guy is the greatest lower bound of B, we needed to show two things. One, it's a lower bound, and two, it's the greatest of them. Okay? So first thing we're going to do is show that this guy actually is a lower bound of B. Okay? Well, what we observed earlier, right? So we want to show that if you have anybody in B, then this guy is less than or equal to it. Okay, right? We want to show this is a lower bound of B, right? This guy is less than or equal to anybody in B. Okay? So, but we saw earlier that anybody in B is an upper bound of L. Right? Anybody in B is an upper bound of L. Right? The supremum is the least upper bound of L. Right? So that means that it is, this is an upper bound of L. This is the least upper bound of L, so it's got to be smaller than that guy. Right? So anybody in B is bigger than or equal to this guy. Okay. So now we've shown the first thing that we want to show. This guy actually is a lower bound. Okay. Yes, Patrick.
Okay, so like yesterday you got to this point, like,
Yeah.
but then instead of that you said that given any other lower bound gamma of B, L, the lowest upper bound L.
I'll do that next.
Great.
I'll do that next. I'm going to do that right now. Okay. So yeah. So I'm doing it in a different order. Okay. Okay. So now we've got this first fact, right? That this guy is a lower bound. And the second thing we need to show is we need to show that that the supremum of L is the greatest lower bound. Of B, right? That this guy is the greatest lower bound of B. Right? It's bigger than or equal to any other lower bound. Right? Right? That given any, i.e., that given any lower bound of B, the supremum of L is bigger than or equal to it. Okay, that's what we want to show now. But that's why is that true?
I have a question.
Oh, you have a question?
Intuitively, I was thinking that it should be the other way around because it's the least upper bound of L, and B, and L is bounded by B. So, I mean, the least upper bound should be less than equal to all the elements in B.
So remember what we're trying to do, right? We've got this supremum of the least upper bound. We've got the least upper bound of L. L is the set of lower bounds of B. L is the set of lower bounds of B, right? And we're trying to show that this guy is actually the greatest lower bound of B, right? The greatest lower bound of B. Okay. Okay. Right. So we want to show that the supremum is. We show that it is a lower bound, and we want to show that it's the biggest lower bound. Okay. Okay, Edward.
Since L contains all the lower bounds of the set B, but gamma sup L is already a least upper bound of that set L.
Right.
You already have the visual.
Yes, exactly. So yeah, we're done already. Right, by definition, right, you say, well, look, right, supremum of L is the least upper bound of B, right? It's the least upper bound of B, right? I'm sorry, the least upper bound of L. Sorry, I'm going crazy here. The least upper bound of L, right? So it's an upper bound for the set of all lower bounds, right? So of course it's bigger than all lower bounds. It's an upper bound for the set of lower bounds. Okay, right? Of L the set of lower bounds of B. Okay, so of course, it's greater than any lower bound of B. Okay, as long as you maintain your sanity, it's simple. Oh, yes, Max.
So going back to the first part of the
Yes,
paper, we
yes.
proved that it is a lower bound.
Yes.
What happens if the supremum of L isn't an element of L? Because it seems like then that proof falls apart.
Isn't an element of L. We're showing that it is an element of L. Right?
Yeah,
We're showing that it isn't. We're showing that the supremum of L is a lower bound of B, right? And so it belongs to L. That's what we're showing.
Got it. Okay.
Yeah.
Okay.
Yeah. Okay. Okay, talk to each other for 1 minute and clear the air. There's some, yeah, talk to each other and see if you can figure out what's going on or make a question that will help you figure out what's going on.
This is, so these
And then, so the greatest lower bound of like is the lower bound of everything on the right, and so that's why it's going to be right first. And then the second one is that, so it's bigger than everything on the left, so that's like the upper bound.
it's just representing all the just bigger.
The middle L is, yes.
Yeah.
Okay, I don't know if this is going to help you, but I'm going to draw a picture. So suppose this is the real line, and you have some set B. Okay. This set B is bounded below, right? Set B is bounded below. And what's L? Well, L is the set of all lower bounds, right? The set of all lower bounds. We're trying to show that there is a greatest lower bound. So what we do is we look at L, which is the set of all lower bounds, right? It's all these guys that are lower, all lower bounds of B, right? And our claim is that if you look at that set and you take the supremum, right, the least upper bound, right, the least upper bound, then that least upper bound of L, right, the least upper bound of L will actually be the greatest lower bound of B, right? Will actually be the greatest lower bound of B. Okay, right. So that's the picture you want to keep in your head. Okay, I don't know if that helps. Right. So the first part of the proof is that we say, okay, well, is it a lower bound of B? Well, right, any element of B is an upper bound of L. Right? Any element of B is an upper bound of L, and this is the least upper bound. The least upper bound of L. So it is going to be a lower bound of B, right? Anybody in here is bigger than or equal to this guy, right? So it's got to be a lower bound of B. Okay. And then the second thing we show is that to show that supremum L is the greatest of the lower bounds, but that's by definition, right? It was the least upper bound of L, right? So it's going to be bigger than or equal to everybody down here. Okay. So in R, if you think about in R, it's very straightforward, right? Now, you just have to make sure that you're not using any special property of R, because we're not in R, right? We're in an ordered set. Okay, so maybe you can use this to help formulate your argument, right? But just make sure that you're not using any property of R, like the fact that it has its greatest lower bound properties. Okay. I hope that clears things up. Are there any questions? Does anybody have any questions? Mr. Al?
This is very fundamental one. The purpose I would want to prove this here is because.
Is that the question?
To establish, yeah, that's the question. Because by doing this, I establish what?
You established that you don't need to think about a greatest lower bound property, right? That whenever you have a least upper bound property for the set, it has a corresponding greatest lower bound property, right? That they're equivalent to each other. Okay, so there's a symmetry to these notions that that if one holds, the other holds. They're equivalent to each. They're logically equivalent.
Thank you.
You're welcome. Okay, so let's go on to the next stuff. So that's all we're going to say about, that was the main thing that we wanted out of introducing ordered sets, this least upper bound property. Okay, so now we're going to move to a different aspect of what will be later revealed as the real numbers, this thing called field. Okay, so fields. Okay, so fields, so the notion of field is a generalization of things like the rational numbers, the real numbers, the complex numbers. So in your mind, maybe you keep the rational numbers, the real numbers, the complex numbers in mind. Okay, but these are not the only fields. There are much, there are other fields. There are more bizarre, different fields. Okay, so the definition is kind of long. Let F be a set with more than one element. So with more than one element. Okay, with more than one element, with binary operations plus and dot. Okay, plus and dot, of course, are the analog of your addition and multiplication, but they need not be what you think they are. Right? They might not be your old friends. We use this notation, but don't be misled by it. These are not necessarily the things you're familiar with. Okay. With two operations plus and dot, such that a whole bunch of properties are satisfied. Okay. So there's sort of a minimal list of things that we want these things to satisfy. One is called closure. So when I write A1, I mean dealing with the additive operation. So the first axiom dealing with the additive operation. So closure, whenever x and y are in F, then x plus y is also in F. Okay. So you don't leave the field when you add things together. Okay. So two, commutativity, right? That whenever you have two guys in the field, then, right, so suppose you have two guys in the field, then it doesn't matter in what order you take the addition, right? It doesn't matter in what order you take the addition. Associativity, you know what I'm gonna write. X plus y plus z is gonna always be equal to x plus 1 plus z, right? Right? Do the x plus y first and then add on z. Or if I add x to the sum of y plus z, then I get the same thing, right? A4, additive identity. There exists an element called 0 in F, such that for all x, x plus 0 is still x. So there exists this guy 0 that when you add it on, nothing happens. Okay, so these are all things that you're...
What about additive inverse?
Yeah, sorry. that's why I'm pausing here. Additive inverse, so last thing, additive inverse. For each x in f, there exists some guy called negative x, also in f, such that x plus this guy negative x equals the 0 element. Yeah, Greg.
Should the 0 and negative additive, like minus x, be unique or different?
We don't have to specify it. It will be. It's a consequence actually that those guys will be unique. Yeah. So yeah, these definitions are kind of as spare as possible. Right? We don't specify any more than we want than we need to. Some things will happen as consequences. Okay, so the way you want to think, is that we're making something, and it's something like the real numbers. Okay, what's a field? It's something that has these properties that the real numbers have. Okay, other things that we want to happen, we want closure. We want closure for multiplication. We want commutativity for multiplication. We want associativity for multiplication. We want the existence of a multiplicative identity. Right? You want something that acts like the number 1, right? Ayolan.
Oh, I have a question.
Yes.
So, what's the relationship to the definition of field to that of a vector space?
A vector space. Vector space is something.
You have similar relations.
Yeah, but for example, you don't have multiplication, right? You don't have multiplication, right? So these things are true in the vector space, but you also in the vector space you also have multiplication by a scalar, right? You've got addition, you also got scalar multiplication, right? And so it's a different animal, right? But we define it in a similar way, right? Yeah, but you don't have any of this stuff. Right? So and 5, multiplicative inverse, right? For all x in the field star, and when I put a star on it, I mean excluding 0. Okay, so this star means the field, but excluding its 0 element. Okay, the field excluding the 0 element, and this slash means excluding. Okay, for everybody in the field, but except for 0, there exists a 1/x, right? In F, such that the product is the additive, is the multiplicative identity. Okay. So let F be a set with binary operations that satisfy all this. Okay. In that case, we call F a field. Just a second. So, examples, like I said before, Q, R, and C are all fields. Right? Standard examples of fields, right? You think about the real numbers, say, right? Well, they addition satisfies all this stuff, multiplication satisfies all this stuff. Oh, I forgot distributivity. So there's one more. D. For all x, y, z in F, x times y plus z equals xy plus xz. Sorry about that. Okay. So there's this one description that involves both the addition, talks about the relation between, the interaction between addition and multiplication. Okay. So I don't call it M or A. In that case, we call F a field. Okay, so Q, R, and Z are fields. What about what if I talk about 2x2 matrices? 2x2 matrices. Are the 2x2 matrices a field? If I add them together, I get a 2x2 matrix. I can make addition commutes. Addition is associative. There's a zero element, right? It's the zero matrix, right? They're additive inverses, right? That's okay. But commutativity, we start to run into trouble, right? So it's not a field. So no, not a field. Okay. What if I ask you about Z mod 4Z? Z mod 4, right? So the number is 0, 1, 2, 3. Where, if you add them, then you loop back to 0, right? So like 3 plus 1 is 0. Like when you multiply, 2 times 2 would be 4, which I go back to 0, right? 2 times 2 is 0, right? Et cetera, et cetera. Is this a field?
No.
So think about it. Talk to somebody for 10 seconds, 20 seconds. That's all you get.
I think that actually what I'm thinking about is like 2 doesn't have multiplicativity.
Okay. Who says it does? Who says it is a field? Who says it's not a field? Why is it not a field? What's your name, please?
Alex.
Alex, yeah. Alex.
2 doesn't have a multiplication.
2 doesn't have a multiplicative inverse, right? There's nothing I can multiply to get to 1 here, right? 2 times 1 is 2, 2 times 3 is 2, 2 times 2 is 0, 2 times 0 is 0, right? No more, I can't get to 1. There's no 1/2 here. Okay. Right, so this is not a field, right? If it's Z over Z mod P, where P is a prime, then it actually turns out to be a field. Okay. Okay. So fields. Okay. Fields. Just to generalize, it's just an abstraction of your old friends Q, R, and C. Okay, consequential properties. Okay, so there are other things that you know about the real numbers that you think, well, why didn't I include these other facts in with my definition? And the thing is that we don't need to include them. They're consequences of the parts of the definition. Okay, so I'm just going to write this up as a proposition. Proposition is usually some sort of like not as good as a theorem, like some result, not that sophisticated. It's like a theorem, but not that great theorem. Okay, so here's a theorem. It says that if F is a field, and X, Y, and Z are in your field, then if X plus Y equals X plus Z, then Y equals Z. Okay. Then you can cancel. Okay, right, cancellation is okay. Okay, so you might think, well, I'd like this to be true, why didn't I throw it in? You don't need to throw it in, it's a consequence of the properties of the field. Okay. Property B, if x plus y equals x, then y equals 0. Okay. Property C, if x plus y equals 0, then y must be negative x. Property 4, the additive inverse of an additive inverse is your original element. Okay. So these are all things that follow from the field axioms, right? The properties of a field. Okay. So things that you think ought to be true, and they indeed turn out to be true. So let's quickly sort of sketch out how these things are proven. So proof A. So the proofs of these facts are not the most exciting. Okay, they're very simple, but they're extremely boring. So suppose x plus y equals x plus z. Okay, so that's where we're going to start off from. And what we're going to do is we're going to add negative x to both sides. So we know x, there is a negative x, right? Okay, then this is true, right? So add additive inverse. Right. So the point is that we're using the existence of an additive inverse, right? If we didn't have additive inverses, this would not be possible, but we can do it because we're in a field. Okay. Then this is true, and then the next boring thing I'm going to do is this, right? And that's true by associativity of addition. Right? What am I going to do next? Next.
0 plus y equals 0 plus z.
Right? So I'm going to say negative x plus x is 0. Right? So 0 plus y equals 0 plus z. Right? And what am I using? I'm using the properties of the additive inverse. Right? That x plus negative x is 0. Right? And then I say y equals z, which I'm allowed to say by properties of 0, right? So properties of the additive identity. Okay. So right, so each of these things has some I'd have to say by A5, right? By A3, by A5, by A4. Right. So this would be, for some, I've heard one of my ex-students said, oh yeah, we had to prove all these in a math camp when I was in high school. I think that probably was the worst experience. What could be the most boring way to introduce somebody to proofs? I think this is probably it. But it's true. This is how you write a proof, right? You say, okay, we want to show that y equals z. You say, well, if this is true, then this is true because of that. This is true because of that. This is true because of that, et cetera, et cetera. And then we get this is what we wanted, and you put a tombstone on it, right? You say the end, right? So this is the traditional way you end a proof. You put this thing called the Halmos tombstone. You thought I was kidding, huh? No, it's true. That's actually the term for it, the tombstone. The Halmos tombstone, after the mathematician Paul Halmos, who made it up. I think he may be dead. I wonder, I'm pretty sure if he is, then this is probably his tombstone, right? He probably has a tombstone in the shape of the Halmos tombstone, I would guess. Yes?
What's the contradiction one called?
It's just a contradiction symbol, and it doesn't have a particular name to it, as far as I know. In LaTeX, it's called by text reference mark / text reference mark. Okay. So that's a proof of A, right? Everybody okay with that? Okay, right. And then take 1 minute and prove B. It's already done. Yeah, I know. Okay, take 10 seconds and prove B. Okay. Who wants to tell me how to do it? Fei Yang, how about you?
Because of B and by additive identity, you can say that x plus y is equal to x plus 0, and using proposition from A.
Exactly. So you say, okay, well, if this is true, then I can certainly add 0 to both sides, and then I invoke A. Right? Then I invoke A. I get x plus y equals x plus 0 because I'm going to add 0 since 0 is the additive identity. Then I invoke A and I say, okay, I can cancel. Right? So I cancel off the x's and I get y equals 0. The other properties are equally as exciting. Okay, so I'm not going to prove them. Okay. So okay. But I should say that in the 17th century, I think, there was some argument about why -1 times why the negative of a negative should be the number itself. Right? Like why is that? And it's not completely obvious unless you think in this way. Then it is obvious maybe. Yeah. So that was something that confused people. I think Leibniz and others argued about this. Yeah. Okay. Okay. Oh, wow. Okay. So I guess I'm also not going to prove the following proposition, which is just some other properties of other consequences. Other consequences of fields. That one, if you multiply anything by 0, then if you multiply anything by the additive identity, then you get the additive identity. Right. So 2, if you have 2 non-zero elements, then their product must be non-zero. Right? Or it's contrapositive. It's the same thing as saying if the product is 0, then 1 of x and y. So at least 1 of x and y must be 0. Right? This is sometimes called the zero product property. Zero product property. Right? Whenever you get a 0 as a product, well, one of the factors must have been 0. See that you can move the additive inverse sign around. So the additive inverse of x times y is the same thing as the additive inverse of the product xy, which is the same thing as the product of x times the additive inverse of y. And d, the product of additive inverses is the product of the original elements. Okay, So there's a bunch of things. You know, the proofs of these facts are pretty straightforward, so I'll leave them for you to read. Okay? And if you find them hard to digest, then come to office hours and we'll unpack them. Okay. So don't feel at all hesitant to come in.
Oh, sorry.
That's all right. I realize I've been recording the floor all this time. I hope what? Did you do that?
Sorry.
No. I don't think I put it on the table. Yeah. No, it's not your fault. Yeah. So if I may, yeah, please feel free to come in and talk. You know, my office is just over there. It's not like when I was an undergraduate and the office of the mathematicians was in this tower at the edge of campus, and you had to trek across. You had to trek across campus to the tower of mathematicians, and then you enter the tower, and it was silent. Right? And people were, you knew that the mathematicians were, at work there, and you sort of didn't want to talk with them because it was very like you didn't want to disturb them, right? And so generally my experience was that I would go and I would sit outside the professor's door and I'd concentrate, so hard, because I didn't want to disturb the professor, right? So I'd like, okay, what am I trying to do? And I'd solve the problem and then I'd go back. I'd go back to learning without ever speaking to the professor. So it's different here, right? You don't have to feel like we're actually happy to talk to you, and okay, so okay, so let's get on with it. The next notion. So those are fields, and we talked about ordered sets, right? And now we're going to talk about ordered fields. Okay, ordered fields. Okay, so you might think an ordered field is a field with an order. Okay, that's not quite true, right? It's not quite true. So definition, let F be a field. If there exists an order on F, and it has the following property, that whenever y is less than z, then x plus y is less than x plus z. Okay, so addition of the same element to both sides preserves the order. Okay, addition of the same element to both sides preserves the order. And also, whenever you have positive elements, then multiplication is still, the product is still positive, right? So the product preserves positivity. Okay, you've got positive elements, then the product is still going to be positive. Okay, so if you have a field, right? So remember, the field has a plus and a dot, right? It has its addition and it has its multiplication. If there's an order, and the order and the plus and the order and the dot work together in this way, right? They jive. I don't know how to say. They have these two properties. Then we call F an ordered field. Okay. Then we call F an ordered field. Okay. One of your problems will be to show that C cannot be made into an ordered field. Cannot be made into an ordered field. Okay, so earlier we saw that C could be given an order, right? Could be given the lexicographical order, but that lexicographical order doesn't work well with the operations of C. Okay, so, and in fact, you'll see that there's no order you can give C that makes it into an ordered field. That's your homework. Okay. Okay. So okay. So blah blah blah. If you have a field and order, and the things work together, then we call this thing an ordered field. So Okay, and the main point of this chapter is the following, that there exists an ordered field. There exists an ordered field that one contains the rational number as a subfield. And two, has the least upper bound property. Okay. And the proof of this is left to the appendix of chapter 1. I'm going to leave it there. You don't have to read it. So the proof is in the appendix. So we're not going to do the proof. We're not going to construct the real numbers from the rational numbers via so-called Dedekind cuts. But if you feel like reading it, you can. Okay. But this field is called R, the real numbers. So it's possible to, one way you can think of it is that it's possible to extend Q, to sort of fill in the gaps of Q so that it now satisfies the least upper bound property. Like it's like Q plus the least upper bound property turns into R. Okay. 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 So yeah. So. So I've skipped over one thing, but again, there's one theorem of basic properties of ordered fields, which I'll ask you to read. Just read it. Okay. So things that you would like to, again, things that you would like to be true, right? If x is less than 0, then negative x is greater than 0. That x squared is bigger than 0, whatever. If x is not equal to 0, then x squared is bigger than 0. They're sort of basic properties that you would like to be true. There's a few of them, and they turn out to be true. Okay, so I'll ask you to read those as well. Again, the proofs are pretty straightforward. Okay. Okay. So next time we'll start with R, and so this is all we know about R. Okay, so don't jump to thinking that you know everything about R yet. All we know about R is that it is an ordered field that contains Q as a subfield and has the least upper bound property. Okay, and from there we'll be able to see some properties. We'll be able to derive some fundamental properties of real numbers. Okay, that's it for today.